Hi everyone, Bill Kinney here. This is a video to alert you to something new and exciting going on at my blog, Infinity is Really Big, that you see here. Just today, May 14th, 2019, I posted my first section of what will ultimately be an online textbook on linear algebra. I'm calling it Visual Linear Algebra Online, okay, and again hosted at my blog, infinityisreallybig.com. I'm aiming to write about one section per week. That's my goal. I may not always make that goal, so please bear with me if I don't quite make it. That's my goal. If you want updates about when the different sections are posted, you can certainly subscribe to my blog. Go down here and click the subscribe button and you'll get new posts by email. Okay? So I want to show you what you'll find in this very first post that you see here right here from May 14th, 2019. Is the main thing I show you in this video. But before I do want to remind you also that about the past month and a half, I've made a bunch of posts, in fact 10 of them so far, on studying for a certain actuarial exam. Actuaries work for insurance companies commonly. They study risk, and exam LTAM stands for long-term actuarial mathematics, and it's one of the exams they have to pass. And it's something I'm personally studying for myself. So I talk about how to learn and think about this content, and a big thing that I do is I make animations like you see here to help you understand the content. Okay, and I'll be doing that with the linear algebra book as well. I'm offering this for you for free and for my students at Bethel University for free. However, if you want to support me, there is a way. I don't have a Patreon page, but I am an Amazon associate. So you could also click on the links to Amazon books if you're interested. One book that I just started posting today is very interesting to me. I just finished reading it. It's this book, Infinite Powers by Stephen Strogatz. Very, very good book, giving you the key insights into calculus and the big picture goals of calculus. And I'll whet your appetite by showing you a really cool graph that you'll find on page 165. This graph right here is showing you Usain Bolt's velocity when he won the world record for the 100-meter dash. And the interesting thing about it, to me, is that the velocity goes up and down real fast. And you wouldn't think about that normally, but that does evidently correspond to the strides that he made as he's going down the track. Okay, so pretty interesting. And again, you'll find a link to that through Amazon on my blog. All right, so let's go ahead and look at this first section now. And with a goal of just sort of helping you see the big picture of what's going on here. The title of the post is Points, Coordinates, and Graphs in 2 Dimensions. And you can essentially think of that as the title for section 1.1 of the textbook. Again, the textbook is called Visual Linear Algebra Online. This is chapter 1. Chapter 1 is ultimately about vectors, matrices, and linear transformations. That's the big picture. Now that might not mean a ton to you. It might mean something and it might not mean much yet. Let me just give you the big picture, and I really do emphasize this big picture in this very first section. The big picture about linear algebra is more than just solving systems of equations. It's more than just doing calculations with vectors, matrices, and linear transformations. It really is about developing tools to help you solve a wider array of problems and to represent a wider array of applications. And the big theme to me in that is the idea of a change of coordinates, new coordinate systems, okay? And to get that across here in this very first section, you can see in the picture here at the beginning of the section what I'm calling a system of slanted coordinates, okay? Now hopefully you are used to rectangular coordinates, and I talk about that in here, but ultimately we're also interested in slanted coordinates. It might not be clear why. It probably definitely is not clear why. Ultimately, as we go through the sections of this book, you're going to see why slanted coordinate systems are useful. Okay? They correspond to helping you solve problems. So let's go through this blog post. I do various things to try to make this as interesting as possible, and you can see here the initial topic is about points. You know, how can points be possibly interesting? Well, I think points are kind of interesting, and I try to bring that out here. I talk about how you might try to define what a point is. You might say a point is, well, maybe a dot like a period, or something really, 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 really small, maybe like an atom or maybe even an electron, a location or a geometric object that has no area, length, area, or volume. And those are things people might answer when they are asked what a point is, but none of them is really good enough as a definition, okay? I talk about, you know, that they're sort of okay and giving you some intuition, but that's not really good enough for a mathematical definition. So the main thing I emphasize here initially is that you really want to leave points as undefined mathematical abstractions and not really worry too much about what they are exactly. However, visualizing points, they do need to be drawn as if they have area. However, you do not want to make that area bigger and bigger as you zoom in. So this animation is illustrating that the graph on the right that you see here is not the way that you should visualize a point. Don't imagine that it gets bigger and bigger as you zoom in. It's supposed to, quote unquote, stay the same size, even though it doesn't actually have any size. Okay, that's the first thing to realize about points. Then I start talking about rectangular coordinates, okay, which is hopefully a coordinate system that you're used to. This initial section that you see here, there's an emphasis on terminology. You'll often hear math teachers, mathematicians talk about the line or the plane, even though there are lots of lines and lots of planes. Okay, that's just a little section to let you know that's not a big deal. Don't worry about it, okay? Don't let it confuse you. A little bit of history here about rectangular coordinates, ultimately leading to them being sometimes called Cartesian coordinates in honor of a Frenchman named René Descartes. There's another Frenchman named Pierre de Fermat who also discovered rectangular coordinates at the same time, but Descartes was the one who had them named after them. So I like to put a little bit of history in my blog post wherever it seems appropriate as well. All right, how do you actually construct rectangular coordinates? Imagine the plane, okay? A plane really, but the plane. You imagine it going on forever. And you want to impose a coordinate system at the start, which consists essentially of two axes, a horizontal axis and a vertical axis that cross, like you see here, at a point that you call the origin. You want to pick a standard of distance, you know, it could be a centimeter or a meter or whatever, and usually it's best to use the same standard on both axes, though you technically don't have to, and there are good reasons not to in some situations, but at first, go ahead and make them the same on both axes like you see here. Once you have set this up, this defines essentially a rectangular grid like you see here, essentially graph paper, okay? Though you imagine this graph paper as being infinite graph paper going on forever and ever in all directions. This defines the rectangular or Cartesian coordinate system. Every point in this plane has a unique address, so to speak, and a first coordinate and a second coordinate, or you could also say an x coordinate and a y coordinate. And how do you define what those are? Here's one way. This visual shows you one way. Take the point P, for example. If you draw this vertical line through P and this horizontal line through P, the intersection of those lines with the horizontal and vertical axis give you the first and second coordinates of P. You can see that the vertical line here through P intersects the horizontal axis at about 4.2, and the horizontal line through P intersects the vertical axis at about negative 2.7 or negative 2.8 or so. Those would be the coordinates, the rectangular coordinates of P, and in fact you see that down here. The rectangular coordinates of those 3 points and P is 4.2 comma negative 2.8. That's called an ordered pair. It's a pair of points with a certain order to them. There's another way to view points, and that is in terms of what I call signed distances, signed distance interpretation, illustrated by this animation that you see here. This point is a moving point, and you can see as it moves, its first and second coordinates change. Focus first on the blue line that's going horizontal back and forth. When the point is to the right of the vertical y-axis, the number labeling that blue line is positive, like right now. Okay, 0.38 there. That's a positive distance. When the point is to the left of the y-axis, you think of it as a negative distance. You see the blue line is labeled with a negative number. So the first coordinate is the signed distance or signed length of that blue line. For the second coordinate, you're looking at the brown line, the vertical line there. When the point is above the x-axis, that is positive. You think of that as an ordinary distance. And then when the point is below the horizontal axis, you think of it as a negative distance, like right about now. Very short time where it's a negative distance. So signed distances is another way to interpret coordinates like that. All right, this section gets into equations and graphs. The point of coordinates, pun intended. There's lots of puns with this stuff. Big benefits, and this is actually something that really comes out in this book, Stephen Strogatz's book. that coordinate systems, rectangular coordinates, it's the subject of analytic geometry, and relating it to algebra was the real key that started the scientific revolution. I mean, of course, there were other things. There was scientific observation done by Galileo, for example. But as far as the mathematics of the scientific revolution with Newton and Leibniz and the people who came after them, they really relied on algebra and coordinate systems a lot. And probably they would not have been able to get as far as they did, and we would not be where we are technologically without coordinate systems. So it really is a big deal. Big benefits of coordinates, and again, you'll find that in this book. Essentially, there's a two-way correspondence. Nice equations, given any nice equation that has a nice graph, I'm not going to say what I mean by nice, and conversely, given any nice graph, it can at least be approximated by a nice equation. So there's a back and forth between the two. Then we get into some examples. The examples focusing on linear equations and nonlinear equations. Now again, this is the subject of linear algebra, so we are ultimately focusing on linear equations in the big picture scheme of things, but we should understand and deal with a few nonlinear equations just in relationship to linear equations. So I define what a linear equation is. Essentially, it's an equation like this: ax plus by equals c. It's a linear equation in two variables, x and y. We will be dealing with three variable linear equations as well. A nonlinear equation is one that can't be put in that form, essentially. Okay? These are not super rigorous definitions, but they're good enough for us. The graph of an equation is the set of the points in the plane that make the equation true when you plug those numbers into the equation on both sides. They make the a true equation. Technically speaking, equations are neither true nor false until you plug numbers in and you see whether you get equality or not. Linear equations have graphs which are straight lines, and nonlinear equations have graphs which are not straight lines, at least in rectangular coordinates, and that's actually important, and we'll see a comparison with polar coordinates later on here. Example 1 is to draw an ordinary kind of graph. Hopefully this is something you've done before. So I go through the steps. Maybe you want to be systematic about it and solve for y as a function of x and then make a table of values, and here we go. There's a graph of that linear equation, and it is a straight line. How about a nonlinear equation? The nonlinear equation here is x squared plus y equals 3. You can once again solve for y as a function of x, make a table of values, and make a graph. There we go. That's the graph of x squared plus y equals 3, also the graph of the function 3 minus x squared. F of x equals 3 minus x squared. It's not straight, okay? It is a parabola, which is a very special kind of curve like this, but it is nonlinear. What about other kinds of coordinate systems? So the first other kind of coordinate system I call a slanted coordinate system. I start by saying, is there anything special about regular rectangular Cartesian coordinates? And yes, it's because they're relatively easy. But must we use rectangular coordinates? For example, do the coordinate axes, x and y axes, have to be perpendicular to each other? The answer is no. Though that does beg a question, is it very useful to consider other coordinate systems? And again, that's the main point of linear algebra, is that it is useful. Here's an example coordinate system, slanted coordinate system. I've kept the v-axis vertical. It's the same as the y-axis here, but I made the x-axis slanted. I'm calling it the u-axis, slanted at a 45-degree angle from the original x-axis. You still call the point of intersection the origin. You still ideally make unit lengths along the axes here. That would be an example of slanted axes. And they generate slanted graph paper. There we go. There's some slanted graph paper that these slanted axes would generate, generating a slanted coordinate system. So now the question is, given any point in this plane, what are its new coordinates with respect to this new slanted coordinate system? They're not necessarily the same as the old coordinates, the old xy coordinates. These vertical lines are where u is constant, and these slanted lines are where v is constant. Given any point like right there, let's say right there, what are its u and v coordinates? I hope you would guess that its u coordinate at this point would be 3 and its v coordinate would be 2. That would be correct. Okay, we can eyeball it for ones that are not exactly on those lines. P and Q here, I'm estimating, the original rectangular coordinates of P are 2, 0, and the original rectangular coordinates of Q are -4, -1. You don't see the x-axis in here, but it would be about here. What are the new slanted coordinates? Hopefully you could estimate them from this picture. And here's how I'm estimating them. P would be about u is 2.8 and v is -2. And then Q would have slanted coordinates, U equals about -5.7 and V equals 3. Okay, make sure you understand why. Double check things. You can transform one coordinate system to another using what you would call a transformation. In fact, this is an example of a linear transformation, though I don't say that. This system of equations that you see here, U equals square root of 2 times x, and V equals -x plus y, takes x and y coordinates and converts them to U and V coordinates. So for example, the original Q had xy coordinates -4, -1. Its UV slanted coordinates are -5.7, 3. Okay, just like we guessed above. You can plug those numbers in and check that. I'm not telling you where the system of equations comes from. You could think about it on your own, see if you can figure it out. You can also go back the other way. You can take this system and solve for x and y in terms of U and V, and you get this other system down here that helps you go back the other way. If you know the UV coordinates, like these numbers here, you can figure out the xy coordinates, okay? So the actual U coordinate of that point was -4 square root of 2, just like I set up here. Graphs and equations can be transformed as well. So example 3 is to draw a graph of this linear equation in the slanted UV plane. Does that mean it would be the same graph as the original? No, it's not actually. You plot the same points, however, you've got the same numbers here, but you interpret them differently. For example, this first point, U is -3, V is 4.4. You don't go -3 along the x-axis and up 4.4. You have to go, you got to go -3 along the u-axis, which means going down here to this point, then up 4.4 like this to get to that point right there. Okay, it's with respect to the UV plane here. It's still a straight line, but it's not the same straight line as before, where this was the same equation with x and y before. It was 4x plus 5y equals 10. You could also wonder if you can represent the original line from example 1 in terms of u and v. And the answer is yes, you can, and it will not be the same equation. You need to use those transformations, these equations right here, to help you do that. Replace x with u over root 2, replace y with u over root 2 plus v, and you will simplify to this thing right here. Okay, it's still a linear equation. This is a linear equation for the graph of the straight line from example 1, not this same graph here. Okay, and you could check that. Example 4 is to do a nonlinear example in a similar vein. Plot this same parabolic equation in the slanted coordinates, and lo and behold, you do get a different graph, but it still looks like a parabola, and in fact it still is a parabola actually. It's not the same parabola as before. Okay, and you can also convert the original graph, the original parabola, to UV coordinates, and you get this equation right there, which you can still solve for v as a function of u. The end of the section is about nonlinear coordinates, the most common of which is called polar coordinates, and here's a polar coordinate grid. For any given point in the plane, its r coordinate, take this point right here, its r coordinate is its distance to the origin, which is 5, and its theta coordinate is the angle that the ray from the origin through this point makes with the positive x-axis. It looks like that's 45 degrees, which is pi over 4 radians, and you typically do want to use radians here. Polar coordinates are not unique. That's something to keep in mind. You can also make polar graphs. And in fact, it gets more interesting because even though this function that you see here is linear, theta and r only appear to the first power, and the numbers here in this table are the same, you graph them differently. The graph is different. It's not a straight line anymore. It's something weird and beautiful. But these black dots here are the polar coordinates that you get on these different values of theta up here and these corresponding values of r. So that's a beautiful thing. You can transform between polar coordinates and rectangular. This set of equations is a nonlinear system that takes polar coordinates and transforms back to rectangular coordinates. And you can also go the other way using the inverse tangent or arctangent function, though you do have to be more careful because the arctangent function always gives you angles in the first or fourth quadrant. So you sometimes have to add pi radians to them to get in the second or third quadrant. So you want to draw a picture as well. At the end here I have some exercises, including an exercise with rotated coordinate system, which you could also think of as being slanted. Both the u and v axes are slanted in this example here. I don't have an answer key for this. I'm not sure if I'll have the time to, Maybe at some point I will, but this is something you can work on, and if you are a teacher, you can assign as well to your students. Thanks for watching.